Hello, and welcome to the last of our kind of introductory or foundational exercises. These introductory exercises are providing information and training on some of the practical tools and techniques that we use within UCal4 while we're developing our calibrations and calibration sets. This last one is a series of 4 exercises. They're all pretty short. They all cover the same general area, which is plotting and graphics. So we put them all together. Plotting and graphics are tools that you will use in UCal4 to help you visualize what is going on with your data sets. If you think about back to, in the introductory lessons in talking about data analytics, and we talked about the data table and a number of response columns, and then hundreds of feature columns. And these feature columns are the wavelengths, the absorbance of your samples at particular wavelengths. And this is just a massive, massive data table. Well, plotting and graphics allow us to visualize some of what's going on with all of this information and to interpret it in various ways, including how the regression is going to be approaching our data. So let's jump into this. So the first part of this is just an introductory to the graphics, and we'll just be plotting out some raw spectra. You can see over here on the right-hand side what an SVF file will look like. You can plot one spectrum, you can plot them all. Each one of these traces or graphs is a sample. And this is really useful just pulling out and looking for extremely unusual spectra, okay? You can see all the samples. You can see some of the features that we've talked about in the past. So please jump into 112, exercise 112, and just plot out the various raw spectra options. From there, we'll look at some math processing features. And before I get into this, and I will show this once we get into the UCal4 demonstration part of this exercise, but there is some really good information in the help section in UCal4 about math processing and about each one of these different algorithm types. So I would encourage you to look up the help section in math processing or math treatments, and you can get more information. So math processing, we're going to use these techniques to help us remove some of the non-constituent effects. So we're trying to focus our entire process on variation that helps us get where we want to go, which is to quantify or qualify a particular constituent or property. We're also trying to minimize or ignore variation in the spectra in our sample sets that does not help us or even might hinder us. So this is almost like filtering out the information that's helpful and filtering out the information that is not helpful. This is why we do it. We do it to reduce the effects of the non-constituent variation. We're focusing on the variation that's going to help us. It can also help us make our regression a little bit more general and more applicable. Okay, and this shows the available treatments that we have. These are math treatments that are available to help us focus on the information of interest. A plot of a raw spectrum. First one we're going to talk about is SNV, or standard normal variant. This is a full spectrum method. You will hear me describe them either as a local method or a full spectrum method. And full spectrum methods look across the entire wavelength range, and they make a calculation for all the data points at once. For this method, you do not need any stored spectra, so you're not subtracting an average from a previous set or anything. It is calculated on the fly. Any noise that's in the spectrum gets distributed across the entire range. So if you've got very noisy areas, it's something to pay attention to. And what it really does is it scales this spectrum. So on the left, we've got a raw spectrum, flower sample. You can see the absorbance values. And over here on the right, you've got a scaled and SNV treated spectrum. It is not centered, that's a default. And you can see that it really just changed the scaling, but the overall shape and features of the spectra remain very similar. Next one we'll talk about is D-trend. This is also calculated across the entire spectrum. And what it does is that it removes the underlying pattern from data. It is in the background a polynomial math treatment. Here's a mathematical formula for it. And looking at it in practice, over on the left is again, a flower sample. And you can see that overall there's a slope to this spectrum. And in general, one of the things we find in reflectance measurements in near infrared is that the slope relates to particle size. It's due to scattering. And for most constituent types, most sample types, scattering and particle size does not help us get where we want to go, which is normally a quantitative prediction of, for example, protein or moisture or fiber. So by doing D-trend, we can get rid of that slope effect and that particle size effect. And it's variation that doesn't help us. Just to note though, every once in a while you will come across a constituent where you do not want to use D-trend. With near infrared, not only can we do properties or constituents or compositional constituents, but you can also do properties. For example, there are very effective calibrations made for digestibility in forages, and that's not due to any one particular chemical or molecule type. Another calibration we can do is hardness in wheat. And hardness in wheat would logically affect the particle size when you grind wheat. So removing particle size effects or slope from your data set might be detrimental if you are trying to predict hardness in wheat. So this is just one of the examples where, in general, we use D-trend. It's used for the majority of reflectance calibrations, but just pay attention to what is happening with D-trend. And if it relates to particle size, if your constituent does, you might want to not use D-trend. You can see over here on the right, when D-trend is applied, that we don't have any slope effects anymore. When we put those two together, which again is our most common math treatment, our raw spectra gets transformed to look like this on the right. Derivatives. Going back to calculus, derivatives are piecewise math treatments. So they are not in a whole spectrum method. They are looking at neighborhoods and looking at segments that are around our data point, and we are calculating a derivative. So it's only affected by nearby data points. The formula is here. We've got a couple of other parameters, smoothing and skipping, and gaps that are also part of how we calculate the derivative. If you looked over on the left, we can see a raw spectrum, and going over here on the right is a first derivative spectrum with a gap of 8 and a smooth of 8. So looking quickly at the raw spectrum, we can see where there's an inflection point right around 1460 or point, right around where my laser pointer is. So at this inflection point in our raw spectra, the slope of that line should be 0, okay? And if we think back to calculus, and I don't remember too much from back then, but if we think back to calculus, we know that the first derivative, we're looking at the slope, and the slope crosses the 0 line right here at 1460. So you can see that we're looking at very similar information. It's just transformed to look at the rate of change of this graph. So functionally, we've got the same information, just presented in a different form. One nice thing about derivatives is that they take away the offset. So if we've got a linear offset with our spectra, and a second spectrum is just virtually the same as this one, but linear offset, the derivative is going to be the same. Derivative math can be very good at taking away variations such as offsets that don't get us where we want to go, that do not contribute to predicting our constituent of interest. Derivatives are very commonly used, normally the first derivative, occasionally the second derivative. Over the last 25 years or so, I I think that if you looked at the reflectance calibrations that are present commercially and in private practice out there, I think that you would find that 70% or so of the calibrations use this math treatment. So standard normal variant, D-trend, and a first derivative with 188 gap and smooth treatment. This over time has proven to be the most effective single math treatment combination there is. And no matter what, this is a really good starting place. I think I know I've said this multiple times, but if when you're getting into your regression, if you've collected a good sample set, you are going to be successful. And if you try this combination, this math treatment, you're going to know in a couple of minutes right away whether you're going to be successful with this calibration or not. You might be able to work it a little bit further and get it slightly better, but you will get most of the way there just with this math treatment. And so it's very useful when you're plotting and looking at your spectra to also look at your spectra with this math treatment, because you are visualizing what your regression is going to see. And if we look at this, we can see on the left-hand side, again, raw spectrum. And on the right-hand side, this is that same spectrum with the math treatment I just described. The last thing that you might want to do after you've explored your different math treatments is to look at wavelengths. And in general, for most products, most sample types, I calibrate with a full spectrum. And I trust that the regression is going to focus and provide larger coefficients to the areas of the spectra that correlate with my constituent of interest, either positively or negatively. And I trust also that the regression process is going to ignore or downweight the areas of the spectra that do not correlate to my constituent of interest. So those will have low, small coefficients. However, there are some sample and product types that you've got areas of the spectra that you just flat out want to ignore. And this is where wavelength selection can be very useful. So wavelengths to look at, says at the top, the wavelengths with the most sample information, and that's in general. Certainly for moisture, oil, and protein, this is true. I would say 1400 to 2400 nanometers. But this is where a lot of our information is found in near infrared. It's also certainly the sweet spot of the instruments, and it's where the most stable information is. Also, historically, if you look back through Unity instruments, this information is very consistent across 1400 to 2400 nanometers. So if you want to create a very general use calibration, this is a good area to look at. However, in some cases, you can't use that full range. So very dark or very high absorbing or very moist samples over 60% water will make the upper wavelength range basically useless. If we remember to the first lecture, the lower wavelengths have higher energy and broader peaks. Okay, so there's more energy, broader peaks. The upper wavelengths have lower energy and more defined peaks, and it's got a higher absorptivity. So at the upper wavelengths, with very moist or very dark or very highly absorbing samples, you've got virtually no signal return. It ends up with your samples either clipping, getting out of the detector range, or being very, very high in noise because your signal to noise ratio is just very low. In these cases, it's best just to ignore those upper wavelengths because it's at best a distraction. At worst, it could be a negative influence on your calibration. And in these cases, you don't want to look at anywhere near that 1940 water peak. So in many cases, we will look at 1250 to 1875 or so, and we will stay away from that big, huge moisture peak up at 1940. Also, if we remember back to our first lesson, the spectroscopy, if you remember, there's a lot of information that is replicated and duplicated across the spectra. So information that we've got way up at the higher wavelength range with lower energy, but more defined peaks, we've got the same information down in the lower wavelength area with higher energy signal passing through. So it's got lower absorptivity, but it's got these big, broad, low resolution peaks. So the information is still present in these lower wavelengths. It's just in a slightly different form. So again, you'll see these spectra where it'll clip. We might have examples, but just if you see an area of the spectra that are not helping you at all, try calibrating and focusing your calibration on the regions that you've got repeatable, high signal, low noise data. Getting to the math processing, it's just the same as the rest of the menu. You just go into the plot, you get to the math treatment. It brings up a math treatment screen that looks like this. Again, if you look at the help, it's going to give you good information. These is the exact same dialogue that you have during your regression. So please keep in mind during this plotting that you are visualizing what your regression is going to see. This is the good starting place that we recommend. First derivative, 1881. And please jump into exercise 113 and explore this area of UCal. There's also an area that we can talk about group properties. So you're looking at your entire data set. And in this area, you can look at, for example, the average spectrum. That might be useful. I think very useful is looking at the standard deviation. So if you've got a calibration set of 150 samples, you can go in and plot the standard deviation of all of those, and you can find the hypervariable areas of the spectra. It just helps you see where the variation is in your sample set. You can also take a look at correlation to a particular constituent by wavelength or data point. And this is kind of interesting, I think, just looking at the regions of the spectra that seem to correlate to your constituent of interest. Okay. So please go in and explore the group property. Sometimes the differences are so small and you might have to jump in and do some zooming. And the last part is the 3D plots, and we've talked about this. Again, this is visualizing what's going to be happening during your regression process. If you remember, we use PCA or mathematical spectral reductions in our PCA, our sample selection, and in our outlier determinations. And also we do a similar data reduction with PLS when we're doing our regressions. It's very useful, I think, to visualize this. Again, I want to take you back to that data table with all of the features, the hundreds of columns that we have of features and data points. It's virtually impossible to understand and to put dimensions in a shape on the complexity and the variability that you have in that data set. But if you mathematically reduce this to a small number of loadings or eigenvectors, you can visualize these in 3D plots and really see these differences by samples, okay? And this is done automatically, and you can get out a PCA plot that looks like this. And we'll take a quick look in just a second. So you can see individual samples, their distance from the means. You can see the variance that is explained by factor as you're stepping up in number of factors. And then there are different options that we can look at. If you right mouse click or context menu in the graph, you've got these options, and you've got some exercises and specific things that we're asking you to do. I would encourage you to do this. This helps you see what your regression is seeing. And visualizing that, I think, sometimes help you make good decisions as you are working through your calibration processes. And with that, we will jump out, and I will pull up UCal 4, and I'm just going to jump right into the exercise, the last one, 115, and we can pull up our sample set. We can go into plot, and you can see some of the options that I talked about in the earlier exercises, the mean, the standard deviations. The difference is how you can relate it to a particular constituent of interest. I'm going to jump into the 3D PCA graph. I will use the math treatment that we've been discussing. send V and D trend. And I will go ahead here and just to show everybody, but if you jump into the math here, it will start talking about math treatments. And this is very useful, I think, to describe what is happening with these various processes. So it describes the different math treatments and what's happening in your different settings with your derivative types, also other data set options, smoothing, skipping, your final mean center. All of this is described in the help section. So I'd encourage everybody to take a look. So getting back to our 3D plot, I've set up my math treatment. I can jump in. It's calculating our principal components of our data set, and it's plotting. It gives the number of factors to use, just accept the defaults, and we're plotting our first 3 factors here. You can see we can go by sample, and the information is here. The amount of variance that's explained per factor is down here. If we right mouse click, the context menu is here with different options, including labeling and copying to a clipboard if you want to make a report or something. And you can see that we can rotate this. And with certain data sets, especially if you plot a secondary file, you can really see trends. And it really can demonstrate the relationship between different sample types in your data set. If you notice, we've got the sample numbering here also. And if you think back to some of the sample management exercises we did, for example, being able to prepend or append sample names. If we brought in samples from a different mill, from a different from a different supplier, and we've identified those, as you work through this, you might be able to see trends and in your data set that relate to a source, a mill, an oven, a grinder. So this is a very, very useful part of the software. So with that, I'd encourage everybody to jump in and go through the graphical and plotting exercise. From this point on, the class gets to, I think, where everybody wanted to get to right from the beginning, but we will jump into regressions. Thank you, everybody.